In this last video, I want to focus on the problem of spurious regressions. Now, to motivate the problem, let's look at some examples. Here, a first example where we have, let's say, data on the CPI for bear in Sweden. And we also know how many bears were killed during hunting. So two series, bear and bear, if you wish. And let's estimate this model where we try to explain the log of CPI based on the log of the bear series. We get these estimated coefficients and also an R squared of 65%, which is actually quite a lot. Now, does that mean that we should be happy with this regression, since we explained quite a lot of the variance of our response? And should we conclude that there is a relation between both series? Well, I hope that the silly nature of this example makes it very clear that this would be nonsense. Some more funny examples can be found on this website, where here, in example 2, let's say there is a claimed relation between the number of people who drowned by falling into a swimming pool and the number of movies in which Nicolas Cage appeared, a correlation of almost 70%. Or take another example, the per capita consumption of mozzarella and the number of PhDs in civil engineering. And you arrive at a correlation of almost 96%. Again, I hope that these examples are silly enough to warn you about the problem that is arising here. Namely that these correlations don't tell you anything. They're spurious. They don't tell you anything about the relations between the series that are involved. And we should be careful with these situations. Now let's formalize what is going on. Let's say that we have two unrelated series, X and Y, and I want to stress that they are unrelated, so they don't have anything to do with each other. Both of them are generated from this AR type of model equation, where the errors are IID in each case and also independent from each other. Let's say that we now regress Y on X. We know that there is a very important difference between the setting where these rows, the AR type of parameters, would be smaller than 1 in absolute value, when we would have the stationary world, and the setting where the rows are equal to 1 when we have the unit root setting. So in the first case, we have the stationary setting, and you can run this regression. Since the two variables are not related, we would also expect that the estimator of beta converges in probability to 0. However, when you have unit roots, then we may end up with a spurious regression, and the regression should not be looked at. The R squared will not tell you anything about the relation between these variables. So let's have a deeper look at what is going on. We start, of course, from our model and the definition of the least squares estimator. So x prime, x inverse here in the denominator, which is just the sum of the x squares. And we have x prime y in the numerator. Furthermore, we know that under the null of a unit root, x has a unit root, and we can express x as a sum of all its errors up until the same time point t. The same can be done for yt. We will then again rewrite numerator and denominator as partial sums of these errors, relate them to a scaled partial sum process, and then rely on the functional central limits theorem. Now, I already put the correct scalings in front of numerator and denominator, but let's verify whether you agree with the scalings. And let's start by this guy over here. So rewrite xt as the partial sum of the errors until time point t. This guy, we know that it needs scaling by root t in order to recognize our scaled partial sum process. And I need an additional factor 1 over t for the width of the interval to recognize a Riemann sum. And then I know that that guy goes to converges in distribution to this limiting distribution where the integral of the Brownian motion squared pops up with the variance term in front of it. Similarly, for the numerator, we have this over here. Start by rewriting xt as the sum of the errors until time point t. Similarly, for yt, rewritten as the sum of the errors until time point t. Both need scaling by root t in order to arrive at our scaled partial sum process. And you need 1 over t for the width of the interval. And then I know that this guy converges in distribution to the integral of the product of the Brownian motions, where again, you should not forget to pre-multiply by the variance of each of the processes. When we put these results together, we see that beta hat converges in distribution to this quantity. So to sum up, what do we have for the stationary versus the non-stationary world? Well, in the stationary world, you could verify for yourself that the estimate converges in probability to 0. That's a very good exercise for you to re-verify. In the unit root world, we just derived here the limiting distribution of beta. Importantly, beta hat does not converge in probability to 0, as we would expect for two series y and x that are unrelated. On the next slide, I include the simulation results, where I show the limiting distributions for the stationary case, for instance, the rows equal to 0.5. And I also show the limiting results for the non-stationary case. First, only for a sample of 50 observations, but we already see in the stationary world here a peak around 0, as we would expect. Not at all in the non-stationary world. Here we just see a limiting distribution. If I would now increase the sample size from T50 to 500, we expect that this guy collapses to a point mass at 0, which is indeed happening. Whereas in the non-stationary world, we still retrieve a whole range of plausible values. What happens if we look at the t statistic? Well, it starts from its regular definition, estimator minus quantity under the null, when we want to test for the significance of beta, and we divide by the standard error. Now, if we rewrite this guy slightly, and we already introduce the appropriate scaling in numerator and also denominator, what do we see? Well, we saw this term already before, the numerator, and know that the appropriate scaling was 1 over t squared. Now, why does the sample variance need a factor 1 over t? Well, here are the details. The residuals actually behave like a unit root process in this case. If I expand this term over here, I'm left with these 3 terms. And for each of these terms, I already derived the limiting distributions. So I need this factor 1 over t here in order to establish these limiting distributions. So when I introduce the appropriate scalings, I have a factor 1 over t squared, 1 over t over here. So I'm actually dividing by root t. So I also need to, of course, multiply by root t in order to preserve this equality over here. But what does that mean? Well, in the stationary world, you can verify for yourself, like we did a couple of weeks ago, that the limiting distribution is just a standard normal one. In the non-stationary world, however, I have this factor root t that is hanging around still. Or alternatively, the test statistic is big O P of order root t. And what does this mean? That means that the test statistic actually diverges asymptotically. As the sample size grows, it becomes increasingly more likely that the absolute value of the test statistic will exceed any arbitrary value. So also the critical value, and hence you will reject the null that beta is equal to 0. In other words, you will find a significant effect, So it appears that the series are related, although that they are completely unrelated. That is exactly the spurious regression problem. You can do the same calculations for the R-squared. The R-squared is nothing more than the fraction of the variance of the response that is explained by the model, as defined over here on the slide. We can take the estimator in front and then introduce scaling in numerator and denominator to arrive at this limiting distribution. Again, the exact form is not important. What is important is that while this guy converges in probability to 0 in the stationary world, it has a limiting distribution in the non-stationary world. And we can illustrate that again from these histograms. First, from a small sample. For the stationary case, you already see the peak at 0 coming up here, although that there is still some small distortion. In a non-stationary world, we get a whole range of values for the R-squared. What happens again if we let the sample size increase to 500? We get our point mass at 0, as we would expect in the stationary world, but still an entire range, a distribution of values in the non-stationary world. In other words, a high value of the R-squared does not tell you anything in the non-stationary world because it just converges to a random quantity if the regression is spurious. Are there ways to avoid the spurious regression problem? Well, yes, luckily for us there are. And we will look into several suggestions in the tutorial. First, we will look at a regression of the series indifferences. Then we investigate detrending, whether that can be used to avoid spurious regressions. And in the last case, we investigate if the problem can be avoided by including lags. That brings us again to the end of this lecture week, where you have everything in place to look at your tutorial assignment. Oh, that's a typo. That should, of course, be the tutorial assignment for week 5. Good luck.